Hi everyone, thanks for coming out to my presentation today. My name is Travis Addair. I'm the lead maintainer of an open source project called Horovod and a co-maintainer of the open source project Ludwig that I'm here to talk to you about today. I also used to work as the tech lead for the deep learning training team at Uber as part of the Michelangelo machine learning platform. And I'm now the co-founder of a company called Predibase, which I'll tell you a little bit about today, but we're still in stealth, so don't tell anyone too much. But between you and me, we'll definitely tell you a little bit about what we're up to. So to start things off, what is the problem that we on the Ludwig team observed in the industry going on today? The biggest thing that I wanted to emphasize is that machine learning today is fundamentally very limited and slow by a number of factors, which mostly have to do with the cost of creating models, and also which is largely driven by the fact that these projects are driven by data scientists who are a very limited resource in most organizations, and there's very limited amount of attention that they can spend on any given problem, right? So what tends to happen is that most of the resources within an organization are diverted to a very limited set of high priority use cases, right? And so to solve this problem in organizations that have a lot of machine learning problems and not as many data scientists and machine learning experts to solve them, typically what organizations do is turn to these sort of black box AutoML solutions out there in the industry. But these also come with their own set of trade-offs. Typically what we find is that while these solutions kind of get you off the ground very quickly, they also have what we would call this dead end problem, where if you try it and it doesn't work for you, there's very limited recourse in terms of what you can do to further refine or customize the solution to your requirements. And so we kind of end up in this dilemma where we need things that are simple in order to make them accessible to organizations that don't have like an infinite number of data scientists. But they also need to be flexible in the sense that if you try it and it doesn't work just out of the box with the first thing you do, you need to be able to customize and extend it in ways that can adapt to solve your specific business need. And so when we start to think about what a solution would look like that kind of gives us this best of both worlds, the analogy that I like to start with is to think about how things have progressed in the data management and data infrastructure space. So as a little bit of a history lesson, if we go back to sort of the pre-2000s to early 2000s time period, SQL was kind of the lingua franca for all data engineering, data infrastructure work that was going on. But of course, we had this moment in the early 2000s where Google released the seminal MapReduce paper, where suddenly we entered this new era of big data and NoSQL. And as a result, the tooling kind of had to go back to the beginning in some ways, where we're doing much more low-level code, writing things directly in C++ and Java to do this sort of data processing. And we lost a lot of the benefits of a higher-level language like SQL because the tooling hadn't yet caught up to the new state of the world, the new kind of requirements that we had. Fast forward a few years, you had a framework like Hive come in, provided like a much-needed SQL layer over a lot of the MapReduce abstractions. And then Apache Spark, which of course is now to this day a very prominent piece of technology in data engineering that sort of introduced a lower level API, but with a lot of like nice bells and whistles attached. But then the really interesting thing I think has started to occur in the past few years when you see this kind of snowflake trend occurring in the industry where things are kind of moving back to this structured data warehouse as opposed to data lake, SQL and schema driven workflow. And as a result, you see a lot of frameworks like dbt that kind of move from this let's write Spark ETLs to do our ingestion of the data to let's write SQL to do ELT. And similarly, frameworks like Arrow and Dask that are unifying the data transformation and data representation process that then enable frameworks like Fugue to sit on top of this that can build these sorts of high-level SQL abstractions over top advanced data processing pipelines as well. Similarly, if you look at how things are progressing in the machine learning ecosystem, what you see is a very similar kind of pattern where before in this case, early 2010s, you had traditional machine learning and frameworks like sklearn that made it very high level and accessible for people. But then when the deep learning revolution hit, largely driven by the AlexNet paper, what we saw was that things once again kind of went back to lower level tools, lower level frameworks, writing a lot more code, in this case in Python, using tools like TensorFlow and PyTorch. And then once again, there was kind of this interesting kind of trend back to higher level frameworks that occurred. And I would call out kind of two moments in particular that had a lot to do with this. One, we had frameworks like Horovod come along that sort of standardized the abstraction for how you can scale the training of deep neural networks. So most of these systems are using stochastic gradient descent. With Horovod, you have a very common interface that allows you to express distributing training for stochastic gradient descent. And then you also had the paper Attention is All You Need, which introduced this kind of transformer architecture, this attention mechanism, which has now become a very core piece of technology that underlies state-of-the-art NLP models, tabular models, and vision models. And so you had frameworks like Hugging Face come out that packaged up these sorts of transformer architectures into a very high-level user-friendly API. And then you have frameworks, modern training frameworks like PyTorch Lightning and FastAI that provide very good abstractions over training loops and distributed training and all these other sorts of things that are very repeatable in general about doing machine learning training. And so the way that we think about how Ludwig, and specifically Ludwig on Ray, fits into this model, this sort of ecosystem, is that when you have the combination of these two trends together of structured data driven by a move from data lakes to data warehouses, ETL to ELT, unified schema and representation, and combine that with these general model architectures, so standardized processes for distributing the training with stochastic gradient descent, state-of-the-art model architectures that are very reusable to lots of different domains, that's where you have the potential to create this sort of declarative or high-level framework that's very flexible, similar to SQL for machine learning, and that's fundamentally what Ludwig is all about. So what is Ludwig? Ludwig is what we call a low-code declarative framework to build deep neural networks. It's open source, popular framework, got over 7,000 stars at this time on GitHub, 60 plus contributors from across the industry. And one thing that we think is really unique about Ludwig is that it's focused on a mixed modality style of training. So we don't just focus on NLP or tabular or computer vision, etc. We like to think of the training in terms of these abstract data types, as you'll see in the slides to follow, that allow us to mix these different data types together into single models and perform multitask learning where we can do binary prediction, regression, text generation, all of these things together in one framework. Ludwig has been battle tested, used in production at Uber, and is now a member of the Linux Foundation AI and Data Foundation. And at the heart of Ludwig is what we call the encoder-decoder-decoder architecture, or ECD. And the way that this works is that instead of thinking about writing your model in terms of like different layers and having like different dimensionalities to different heads and tails in the model and different stacks of convolutional layers, etc., what we do is we just think about data inputs and data outputs. So with Ludwig, you might say, okay, this particular column in my data set is a categorical column, or this is a text column, etc. And then what Ludwig will do is it will preprocess that data, encode it into a representation that is understandable by the deep learning framework, and then it will combine all of these different inputs together using this combiner layer, do some processing of it, and then decode them into the outputs of the model that you want to predict. And this ends up being a very flexible architecture that is extensible to a wide variety of problems. So for example, if you have some textual inputs and you want to predict some numerical value, that's a classic regression problem. If you have some text data and you want to predict a category, that would be like a text classification problem. Similarly, if you have like two different audio signals coming in, you want to determine if the two signals are the same, that could be a speech verification problem, and so on. You can imagine extrapolating this out to all different types of problems that you might want to solve. And so fundamentally, this gets back to the heart of our original problem, that idea that machine learning is both slow and also these black box solutions are not very extensible, by bringing this declarative model where instead we combine the best of both worlds in terms of the flexibility of a framework like TensorFlow and PyTorch with the simplicity of an AutoML solution. And this is what we call declarative ML. And to give you a better understanding of why we feel that this is a very valuable contribution, here's a quick example. So with Ludwig, you abstract away the complexity of how you scale your model with something like Horovod, how you optimize it with something like hyperparameter search, how you productionize it using something like model serving. And instead, you just express your intent in terms of what you want, and then Ludwig does the hard work of figuring out how to achieve it, right? And so the nice thing about this is that if you do want to provide a lot of specificity in terms of, say, what the learning rate is or what the optimizer is, all of those features are available to you. But if you just want to say, here's my data, train a model, that's also a possibility. And so we give you the full spectrum of going from low code to high code, depending on what your requirements are and what your level of sophistication is with deep learning. And the nice thing about this is also that, because Ludwig packages up all these state-of-the-art techniques into one system, you get all this for free without having to re-implement yourself, like, say, the latest NLP model or the latest, tabular model. So with Ludwig, for instance, we have TabNet as a recent contribution to the framework that achieves state-of-the-art accuracy on a number of different previously very difficult for neural networks problems like forest tree cover, Higgs boson. And as you can see, we achieve parity with the accuracies reported in the original TabNet paper. But that's also extensible to NLP problems as well. So we package up Hugging Face transformers, for example, as optional encoders you can use for text features. And with these, you get all these different model architectures which achieve state-of-the-art results on a variety of data sets. And this is all available to you for free with Ludwig. So instead of having to rewrite this yourself, you just pull the latest version of Ludwig and you get all these new models for free. So this transitions into a little bit more about the benefits of declarative, not just for being able to use new model architectures, but also for being able to scale in ways that were previously not possible. And that's what fundamentally Ludwig on Ray is all about. So in the original implementation of Ludwig, we were very much focused on kind of the single machine, like development on your local laptop way of doing training, right? So what we would do is we would take your data set, which resided on local disk somewhere, the configuration that we showed before, and then we would read the data into memory using pandas, transform it into NumPy arrays, do training on TensorFlow, and then evaluation in TensorFlow. And this had a few limitations, one of which is that the data in pandas has to fit inside memory. It doesn't do any out-of-core processing or anything like that. And with TensorFlow by itself, you don't get any distributed training, so we're processing on a single machine. And similarly, all the evaluation was happening on a single machine, which was running locally. Now, with Ludwig on Ray, recently introduced in v0.4 of Ludwig, what we've been able to do is, given the same config, so making 0 code changes to your application, what you can now do is use Ludwig on Ray, which provides Dask for doing pre-processing, Horovod on Ray for doing distributed training, and then Dask on Ray for doing evaluation. And as a result, what we're able to do is process very large data sets using out-of-core execution, parallel execution, all on top of Ray. We're able to ingest data directly from remote data sources like S3 or from warehouses like Snowflake, do the data processing, transform it into transform data and store it as Parquet, where we then do Horovod for doing distributed training, so Horovod on Ray. And finally, we do distributed TensorFlow using Dask to do parallel batch prediction as well. And all of this can be initialized from your local machine and then executed remotely on Ray using the kind of infinite laptop abstraction that Ray provides. And so configuring Ray to use Ludwig is also very simple. It's nothing special for Ludwig, but this is an example of a configuration that you might typically see when running distributed Ludwig on top of Ray. So here I define my cluster, I specify my cluster name, I have how many workers I want to use, in this case 4. I specify the Docker image, and in this case, what we do is we actually publish GPU array images for Ludwig every night and every release, which you can download from Docker Hub. And typically what I'll do is I'll use a CPU instance here. These are EC2 instances, of course, on AWS. And this will be a CPU instance for the head node, and then my worker nodes will be GPU instances here that are using 1T4 GPU, right? And running Ludwig versus running Ludwig on Ray is not all that different. Running Ludwig, you just say Ludwig train, you give it your configuration file, and you point it to a data set. And then similarly, if you want to run Ludwig on Ray, you do the exact same thing, but with two additional modifications. You first need to instantiate your Ray cluster, of course, and then you need to submit the Ray training function to the Ray cluster for execution. Another feature that we added to Ludwig for v0.4 is hyperparameter search using RayTune. And with this, you can take the same configuration that we saw before and then explore different hyperparameters in parallel using the state-of-the-art RayTune library, which provides lots of different algorithms out of the box. And all of these are made available to you using Ludwig with just a few simple changes to the config, as we'll see here. So if you want to do hyperparameter search with Ludwig using RayTune, you just specify the parameters you want to tune, and then you can optionally provide some constraints over the space to explore. You specify what your goal is. In this case, I want to minimize the training, and then you also, or the loss, and then you just specify the executor and sampler that you want to use, in this case, both the standard defaults for Ray. But this, of course, like anything in this declarative Ludwig style that we've discussed, can be customized as well. So if you want to use a specific search algorithm, in this case, BOHB, a specific scheduler, specify how many samples you want to use, anything that you can do using RayTune in the config, you can specify it here in the hyperparameter search or hyperopt config portion of Ludwig. And finally, I also want to call out some AutoML work that we're doing. This is a bit experimental at the moment, so some of these APIs are subject to change. But what we're doing is taking this same idea of building on top of this idea of hyperparameter search using RayTune and doing distributed training with Horovod on Ray, with Dask and Ray and Horovod. And what we're doing is providing this auto-train API on top of all these things that will allow you to, instead of specifying the complete config, just specify the target that you want to predict. And then Ludwig will do the hard work of running the hyperparameter search and figuring out what the best parameters are in order to achieve the results you're looking for. And there's some work going on in conjunction with some folks at Stanford right now in order to, that will be exploring exactly the techniques that we're going to be using for doing auto training and benchmarking the different hyperparameter search strategies on different model types and data sets. So look for that later this summer as well. And last but not least, I want to briefly talk a little bit about the future of Ludwig and what we're doing with our new company called Predibase. So Predibase is started by the two people from Uber AI, myself and Piero Molino, who's the original author of Ludwig, as well as some other folks, Devrit Rishi from previously a product manager at Google, and Chris Ray from Stanford. And the idea behind Predibase is that we want to take these ideas at the heart of Ludwig on Ray and sort of find a way to bring them to the enterprise with a focus on quick productionization and getting models to derive value for your organization with very minimal overhead. So specifically, we want to bring the simplicity and flexibility of the declarative ML that Ludwig provides with the scalability of Horovod on Ray, and combine that with your existing data infrastructure to create this new type of abstraction that we call the predictive database. And so, as I said, we're still in stealth, so I don't have too much to show you yet about what exactly this means, but to give you a very quick sneak peek, what you can do is you can imagine that we fundamentally want to make the machine learning process as simple and fast as writing any query in a language like SQL. And to do that, we provide some tools that sit on top of your database that integrate very directly with Ludwig and Horovod and allow you to express the intent of what it is you want to predict using a dialect that should be very familiar to anyone who's ever worked with SQL. So for example, in this example here, if you have a customer table in your database and you want to predict which of your customers are going to churn, instead of having to think about some elaborate process to pull the data out, train a model, figure out how you're going to scale the training using the resources you have, how to productionize it, how to serve it, you just simply say, given the data from my customer table, filter it by some standard SQL predicates, and predict the target that I want to predict, in this case, churn. And so we'll have a lot more to say about this in the coming months, but please reach out to me, travis@predibase.com, if you're interested in hearing more about this. And definitely for anyone out there who is really interested, we are hiring, so please reach out to me if you're looking for a new job as well. And with that, I want to thank you all for taking the time to come out and listen to my presentation today. I hope that you'll go and check out Ludwig and tell me all about what you think about it. Feel free to reach out anytime, and thanks again.